Okay, so welcome to our lecture today. Yes, so welcome. Yeah, I have no big announcement to make today, so nothing fundamentally new or so. Yeah, one tiny thing regarding the video recordings for the lecture, because several students asked if I can continue to upload the video. Yeah, I decided to provide the video of the lecture until reading week. So I will do it until reading week, and after reading week I will reevaluate. But as long as I would say attendance rate do not drop to very low levels, I probably do it for the whole semester. Okay? So, but at least until reading week, I will upload the video of the lecture on Moodle. Yeah, other than that, nothing new. Please keep in mind the deadline for the term project. I have not heard any news about conflict for the midterm, so I assume that there are none. If there are some, you should have let us know earlier, but still, let us know if there is any issue. Good. So, last week, we have finished the unit 1, which was the general environment chapter, where we talked about how to invest, where to invest. We talked about things like trading places, regulated stock exchanges, versus OTC trading, versus dark pools, for example. We talked about the process of investing. We talked about things like buying on margin, short selling. Okay? So, starting from today, we will become a bit more theoretical. So unit 2 will start with portfolio, where we start to think about portfolio theory. We'll first start with a chapter on portfolio statistics. So this portfolio statistics chapter, most of the content should be known to you from core statistics courses or even from your school time. So what I try here is to apply those concepts a bit more closely to investment and to what we actually do in that. But there is, I guess, nothing completely unknown. And after that, we will directly jump into portfolio selection or Markovic portfolio selection model and start kind of the core of the course. Good. So, let's assume we have a single asset. We invest in this asset. The core problem and why investment is difficult and why we're having this course is actually that there is uncertainty. Right? And if we invest in something today, we have uncertainty about its future value. We don't know how the stock of Microsoft, Tesla, whatever performs over the next year, which creates uncertainty, which makes investment difficult. So actually this at the beginning here is just a formal way of saying that. So formally what we do is we have an initial investment that we call I. And so we invest this initial. We invest I for one period. So it's a simple one period game. And after the one period we have W, the end of period left. I and a period W. So we can easily calculate the rate of return, which is W minus I, so change in wealth scaled by our initial wealth. So now it becomes quite clear that if we know W, I mean things are very easy, we know the rate of return, and basically we simply invest in the asset that gives us the highest rate of return. In reality, of course, we actually never know W. W is unknown, there is uncertainty. So we don't know what period, end of period where W will be. So now we have to find a way to deal with this uncertainty. How can we deal with that? Well, one way would be just to guess the expected return. So I will ask you, like, imagine there's a stock of Tesla. What do you think? What would be the return of that stock over the next 1 year? Then you can think, well, I don't know, maybe 10, maybe 20%, something like that. But if you start thinking about it, what will be the return of Tesla over the next year? You will immediately realize that this is a very difficult question. I mean, it's very hard to even think about it. I mean, where should you start? So what we actually now have to do or can do to make this task a little bit more manageable is we could create different scenarios and make the question a bit more concrete. So instead of asking, what will be the return of Tesla over the next year? I could ask, imagine the world is in a great economic condition. What do you think, under this condition, the return of Tesla will be? Or I could ask you, imagine the world is crashing, like the economy, like a big depression, what would be the return of the stock of Tesla? Of course, this would still be difficult, but it would be more manageable, and it would be easier to think about it compared to just the average return of Tesla. Okay? So that's actually the idea behind this table. Instead of saying like the return is 5%, we say that for a given state, like excellent economic condition, good, poor, or crash, we think that the return will be 31, 40, minus 6, or minus 52%. Okay? And this is just an example. We could easily extend this table to 20 rows, 40 rows, 50 rows. And you could come up with own ideas for states or scenarios. And those scenarios could be general economic conditions, or they could also be stock-specific conditions. Like, I don't know, the worldwide demand for electric cars increases by factor 10. Or the worldwide demand for cars reduces to 0 because somebody invents a better technology. So it could be general conditions, or it could be stock-specific conditions. And then for each of these states, what we actually do is we also can assign a probability. Because some of these states are more likely than others. So we could say, look, a good economic state has a probability of 45%, a crash has a probability of 5%, and so on and so forth. So, yeah, long story short, we create this table, which gives us a more intuitive, a more conceptual way to think about our expectations of the return of a risky asset. Okay? So if we have this table, we are unfortunately still not very happy because this table is not very convenient. Imagine you have two stocks, I don't know, Tesla and BMW, and you want to decide whether you want to invest in BMW or Tesla. If you have if you have those two tables, it will be actually pretty difficult to compare BMW and Tesla because you have to look at so many numbers at the same time. Imagine the table is 100 rows. I mean, how do you compare BMW and Tesla then? People are pretty bad. People are pretty bad at processing many numbers at the same time.
We can look at the mean and also the area good.
Right.
How much they weigh.
Right.
People want some metrics to be something.
That's the next step, yeah. But the first step is we will need to come up with numbers, metrics that summarize this thing. Okay? Because we don't like these large things. They are a pain to work with. So the first, as you said, the first metric, the first measure that we will use is a measure of location. And this is the expected return. The expected return is nothing else than the probability-weighted average across all the states. So in our simple table, we have only 4 states, but you could do exactly the same thing if the table had 100 states, or 200, or 500. So expected return is the sum over the return in every state, probability weight. Very simple. So if we do this for the example that we have, it's 25% was the probability for a, what's it called, an excellent state, probability for an excellent state, times the return in an excellent state. We do this for the other states too, and we get an expected return of roughly 10%. Okay? So this is the first important measure, the measure of location expected return. I mean, obviously, this measure alone is not a good description of this table. Because if you look at the table, actually no state the return is 9.7%. It's always different. This is just the average. But the actual return varies, fluctuates around that mean. So we need a second measure. And the second measure needs to capture how much the return fluctuates around the mean, which we will later define as the risk index. Okay? So the second measure, which measures the dispersion of the returns in the different states, is the variance, or standard deviation. Conceptually the same thing. So the variance, mathematically defined, again very easy, the variance is the sum of the probability-weighted expression here, and the expression here is the return in a state minus the expected return squared. Okay? So what you easily see is that if the returns are close to the expected return, then this expression will be small, the square root remains small, and variance will be small. If the returns vary a lot, if they fluctuate a lot, I mean this expression will become large, positive or negative. You square it, so the negative one also become positive. It doesn't matter if something is below the expected value or above. It will be large, and the variance will be large. Right? So that's the idea behind the variance. It measures the fluctuation, the dispersion. So if we do this for our example, let's again do it for the first state, the excellent state. We have a probability of 25%. In that state, we have a return of 31% minus the expected return of roughly 10% squared. And we also do that for all the other states. That's our variance. Super simple. So, how would this table here look like for the risk-free asset? So we have the risk-free asset, and the risk-free asset has a treasury bill rate of, I don't know, 3%. How would this table look like? What is the return of the risk-free asset in the excellent state? 3%. Right.
Do we assume that we have a report at a certain price of 40%?
Yeah, we already invested it. We assume that we're just interested in over the next one period, assuming there is an accident state, a crash state, what will be the return of the risk-free asset? It doesn't matter whether we want it or not. But yeah, it will be 3% in the excellent state. And what will it be in the crash state? 3%, right? It's a risk-free asset. It's risk-free because there is no risk, meaning it always delivers 3%.
When a crash occurs and people stop their stock and buy bonds, so effectively the bond price will go up, and then so when we sell in that year, then we can get more money than what we.
Yeah, but the risk-free asset does not necessarily change. I mean, what you say is that the risk-free rate changes over time, right? But if you want to know, if you invest now in the risk-free asset for 1 year, I mean, you fix your yield maturity now. You keep it and you return it at the end of the 1 year, you get exactly your yield maturity. So, I mean, I know where you are trying to get at, but this is a bit too complicated for a simple example. So the risk-free rate, and this is not theoretical, but this is true. If you invest in a 1 year time deposit with your local bank, I mean, what you get in 1 year, exactly the amount you invested plus the promised interest, right? And this doesn't matter whether the world crashes or not. You always get it if it's fully risk-free. So, for the risk-free asset, the return in every state is actually the same. Which means that the variance obviously is 0, which is why it's risk-free. No variance, always the same. For risky assets, of course, this is not the case. For risky assets, we have a different return in every different state. We can have a different return. Good. 2 measures. Expected return, variance. First measure of location, measure of dispersion. I think this is all quite clear. So here, this is the first moment of the distribution. This is the location, the most likely value in the distribution. This is our expected value. The second value, our measure of dispersion, measures how broad the distribution is, how spread out the values are, how dispersed the values are. So if you think about the blue distribution and the green distribution, both are normal distributions, but the green one has a much larger variance, much more spread out. Blue and green here have the same variance, they have just a different location, different average, different expected value. They're 2 different things, location and dispersion. I'll get back to that in a second, but a crucial assumption here is, and we will have to make this assumption, that returns are normally distributed. If returns are normally distributed, actually those 2 moments, the first and the second moment, fully, completely describe the distribution. Okay? Actually, for single assets, it would not be so necessary to assume normality. We could also use more complex distributions. We could use 3rd or 4th order moments. The reason why we typically always in this portfolio context assume normality is that things become very tricky if you combine risky assets into portfolios and if you do not assume normality. Okay? If we combine different assets in a portfolio and then we assess the risk and the return of the portfolio, we will have to assume normality, normal distribution, a Gaussian distribution. Otherwise, things will become mathematically very difficult. Okay? So the advantage of using this normality assumption is really that things become mathematically very easy. So we only need 2 parameters to describe a distribution, which is the mean and the variance. That completely describes the distribution. we don't have to care about higher for the moment, such as skewness, kurtosis. I'll get back to that in a second. We don't need that. Normality, just two parameters, mean, variance. And in this scenario, under this assumption, the variance completely describes the risk because it measures how spread out the distribution is, how strongly the fluctuations are. And under the normality assumption, this is completely described by the variance. Is the normality assumption a valid assumption? Well, yes and no. I'll show you some empirical evidence later. There will be good news and bad news. The good news will be that in our context, for portfolio theory, it seems a relatively reasonable assumption. It's still an assumption, it's not perfect, but it seems quite reasonable, actually. The bad news is that there are other applications, especially risk management, and for those applications, it's in some way a terrible assumption. It's really dangerous assumption. So whether this assumption is valid or not will depend a lot on the context of which we use it. So, let's now think about our portfolio. Assume our portfolio consists of those two risky assets. And we assume that both are normally distributed. So risky assets both are normally distributed. So those two risky assets we just call it X and Y. So 8% of our wealth are invested in X and B% in Y, and B is 1 minus A. This just means that we invest all our wealth in X and Y. We split it between those two. So, what is now the mean and the variance of the resulting portfolio that consists of X and Y? The mean, or the expected return, is actually very simple. It's just a weighted average. So expected returns or returns in general are very easy to deal with because, they are simply weighted average. So the expected return of the portfolio is the expected return of X times A, the fraction we invest in X, plus the expected return of Y times B, the fraction we invest in Y. Unfortunately, things are not as simple for the variance. So the variance of the portfolio is not just a weighted average. The variance of the portfolio is not just a linear combination. For the variance of the portfolio, we have to consider actually the covariance between these two assets. So what do I mean by covariance? Well, covariance is basically a measure of how much two random variables move together. So let's say the horizontal axis here, these are historical returns of X, and the vertical axis are historical returns of Y. So that's just how we define it. And then we look at history, at the returns, and we put all the historical returns as blue dots in here. And this is what we get. So this now shows us that if X had a high positive return, it was very likely that Y also had a high positive return. And if X had a negative return, it was pretty likely that that Y also had a negative return. Of course, not perfectly. So if X has a slightly negative return, Y could still be positive or negative. It's not a perfect correlation. It's not like one goes up, the other always goes down. But if one goes up, the other has a higher likelihood of also going up. And if one goes down, the other has a higher likelihood of also going down, if the correlation is positive. Of course, you can also have a negative covariance or correlation. So then it's just the other way around. So X is a very high positive return, then it's likely that Y has actually a negative return. And obviously you can have situations where there is no covariance or no co-movement. It's just kind of randomly spread out. If you know X has a positive return, you actually don't know what Y is. It's just unclear. 50% chance high, 50% chance low. Of course, I mean, there is not only positive, negative, and weak. I mean, covariance or correlation has an exact number. Right? I mean, there's a correlation coefficient, and this measures exactly how strong the correlation between two random variables. And this covariance, this will actually be very important because the variance of a portfolio is actually the variance of Rx plus the variance of Ry, both weighted, plus this term. And this is 2 times AB times the covariance. Okay? So again, the covariance, the variance of a portfolio, is not just the weighted average. And yeah, this is the formal definition of the covariance, but that's not so interesting for us now. Let me just give you a bit of an intuition why the variance of a portfolio cannot simply be the weighted average. Okay? And I like to use an example that is not in the context, directly in the context of investment, because I think it's kind of a stupid example, but it's kind of easy to remember. Okay? So imagine you own an ice cream shop in Central. It's not an actual shop, it's just one of those trolleys where you sell ice cream. Okay? What is a core risk factor? What is a key risk factor for your business? Let's just assume rain. Because if it's raining, people stay home or people don't eat ice cream anymore. If you have your ice cream trolley, your ice cream shop, it's actually pretty risky. Right? Because if it's nice weather, people buy a lot of your ice cream. If it's raining, more people don't like ice cream. So what could you do to reduce your risk?
Sell some other products that
Yes.
people use in rain. Grab umbrella.
Right. Sell some complementary product. Umbrellas, for example. So next to your ice cream trolley, you set up another store that sells umbrellas. Now actually your overall business that consists of those two stores has lower risk. Because if it's sunny, people buy ice cream. If it's rainy, people buy umbrellas. So you kind of smoothen your cash flows over time. Okay? And this example, as stupid as it is, shows a very important thing. If you only operate the ice cream store, or if you only operate the umbrella store, both are by themselves quite risky actually. But if you combine them, the risk actually goes down. It's not additive. And this is the so-called diversification effect. Right? This is basically actually the fundamental idea behind all portfolio theory. If you invest in different assets that have not perfectly correlated cash flow or returns, you can reduce your risk and you can be actually better off compared to investing in single risky assets because of the diversification effect. Okay? And one easy way to remember it, I think, is really this ice cream umbrella example. That makes this very intuitive. And by the way, of course, I mean, the ice cream umbrella example is designed in an extreme way, so that the covariance, the correlation is negative. In order to achieve a diversification benefit, you do not need a negative correlation. You can also achieve a diversification benefit if there is no correlation, or if there is even positive correlation. The only case in which you cannot have a diversification benefit is if two risky assets are perfectly positively correlated. That means one goes up, the other also goes up all the time. In this case, there is no diversification benefit. But that's like the extreme case. In practice, there is nothing that is perfectly one-to-one correlated. So actually, even if you combine risky assets that are highly correlated, you can achieve a diversification goal. And at the end of the day, when we are done with all portfolio theory, this will be the core result. Hold a portfolio that is as diversified as possible. And this will be the optimal choice. Holding individual assets will be a bad decision, in these models at least, because then you cannot benefit from the diversification bonus. Here? So that was the intuition. Now comes the more mathematical part, but it's really, super trivial. So why is this formula exactly looking at like it looks, as it looks? And I want to show you where this is coming from. This is not coming out of nowhere. Because this is so important, so we should probably spend 2 minutes thinking about it and looking at it. Yeah, I know that like looking at formulas is not the most exciting thing to do probably, and sometimes it's a bit hard to follow in real time, but this is really simple, so if you take 3, 4, 5 minutes at home to look at it, I'm sure it will be clear. Okay? So let me try to walk you through it a little bit. So this is what we already know. This is the expected return, and this is the variance, the general definition. The expected return, probability weighted averages across the different states. The variance, again, probability weighted sums of these deviations. And there is just one way of rewriting it. So instead of sum probability weighted, we can just use the E expression for the expectation, which is the same thing. It's just a nicer way of writing it. The expectation means the sum of the probability weighted states. So then we look at the portfolio of two risky assets. The two risky asset portfolio, again, I think X and Y. Yeah. We invest A in X and B in Y. To realize returns, very simple, just the weighted average, nothing interesting. Expected returns, again, very simple, just the weighted average. The covariance, yeah, this is just how the covariance is defined. It's taken from statistics book. It's just the definition of the covariance between two random variables X and Y. So nothing interesting so far. Same here. Covariance is closely related to the correlation coefficient. So the correlation coefficient is the covariance scaled by the standard deviation. Just a mathematical definition. So now let's start. What is the variance of the portfolio that consists of those two risky assets? Well, the variance of the portfolio of two risky assets follows the variance formula for, like all other things. So it's nothing else than the return of that portfolio minus the expected return, probability weighted across all different states, which is indicated by this E. And that's squared. I mean, that's exactly our variance formula. Yeah? So now what we do is we set in for RP and ERP the values from above. Because we know RP is the weighted average, and ERP is also the weighted average. Nothing complicated, we just do that. The next step is just a tiny restatement. Again, very simple, and I try to do it slow here. So we bring the A terms together, and we bring the B terms together. Okay? So ARX and AERX, we put them together here and put the A in front of the bracket, and we bring the B terms together, BRY and BERY. We put the B in front of the bracket. That's a tiny restatement. So the next step is that we want to get rid of the squared here. We don't like the square too much. We want to get rid of it. So how can we do that? So now we have to be not careful. But if you look at it, it's actually nothing else than a binomial formula. So this is the A expression, A plus B squared. A plus B squared. So what is A plus B squared? I mean, remember school math knowledge. A plus B squared is A squared plus B squared plus 2AB. Right? what we all learned some time ago. So let's do that. So this here is a squared. This is a, the a term. Don't get confused. We have an a here, but I mean this is the a term. It's a plus b. The a term squared plus b term squared plus 2ab. So once we've done that, we are nearly finished, and we nearly have developed the formula. Only 2 more steps. The next step is just a restatement again. So what we do now, and something that we don't like too much, is that there is an expectation in front of the bracket that applies to everything within the bracket. So instead of writing the expectation here in front of this large bracket, we try to bring it within the bracket. To make things a bit more clear what is actually going on. And when we do that, we can actually put terms that are not affected by the expectation, deterministic terms, in front of the expectation. Because A and B, those are the shares of our wealth that we invest in X and Y. So this is not affected. This is the same across all states. Right? I mean, this is predetermined today. There is no expectation of that. The expectation of A is A. It's the same in every state. So that's why we can put the A and the B in front of the expectation. It's the same across all states. The expectation of A is nothing else than A itself. So when we do that, we bring A to this term here, put the A squared in front of it, same for B, and we bring the expectation here, and the 2AB we can put in front of the expectation because, again, that's the same across all the states. Okay? Now we are actually done. Nearly. So this is the formula for the portfolio variance. So far it's a bit ugly. We don't like it how it looks here because, yeah, it's long and it's hard to understand. So the last step is really to realize that many of the expressions in that formula are expressions that we already know. Okay? What do I mean by that? Well, just look at this expression, the expectation of Rx minus ERX squared. I mean, what is that? That's the variance. And I mean, that's exactly how the variance is defined. Here, variance. So it's actually a squared times the variance of x plus b squared, and here again the variance of y. And what's this ERX minus ERX and so on? Yeah, that's nothing else than the formula. And then we just do that. We write the variance instead of this term. We write the variance instead of this term. We write the covariance instead of this term, and that's the formula I just showed you. That's it. And I mean, you can write it in 2 ways, and people do it, I think both are very common. You can write it in covariance terms, or you can write it in correlation terms, which is, of course, completely equivalent. Some people prefer the covariance here, and some people prefer the variance, the correlation, and the 2 standard deviations. Just covariance equals correlation times sigma x times sigma y. Okay? So, yeah. I really try to spend some time on that because people sometimes get confused, well, where this formula is coming from and how you should know that this is portfolio variance. I mean, actually, it's easy to see, right? I mean, you just use the formulas from basic statistics, set in the start, restate a little bit, and this is your result. Okay? Clear? Good. So let's do an example. Things. This table, we came up with that. So far we have not really spent too much time thinking about how we can actually find the values in the table. They are kind of different for the moment. So these are 5 different states of the world. We have two assets, x and y. Each of them has the same probability, and for each state we have an expectation about the return of x and the return of y. So we have a -3 in the first state, 9, 15 in the second state, and so on. Exactly the same table, it's exactly the same idea as the table we had on the first slide, only that we have 2 assets. Okay? So what is the expected return of x and what is the expected return of y? Well, yeah, I think it's clear by now, so we don't have to go through that in detail. It's 10 and 8%. Probability weighted average across all the different states. Same for the variance. Probability weighted, 0.2 probability. This is the return of x in the first state. This is the average, the expected return squared, induced for all states. We have 0.076, and for y, it's 0.0708. Then we can do the same thing for the covariance. Again, we can set in the values in the formula. I'm not reading it out now. And we find that the covariance is -0.022. So this already implies that this negative covariance already shows that there is great risk reduction potential if we invest in low tests. Right? Remember, the correlation of covariance does not need to be negative to achieve risk reduction potential. But of course, the more negative it is, the greater the potential is. Okay, you can also do it with a correlation. The correlation coefficient is between -1 and +1. Even if the correlation is 0.99, there is some benefit. But of course, the benefit is small. So negative correlation, really good potential for risk reduction. And this is what we do in the next step. In the next step, we actually look at portfolios that consist of x and y. We build portfolios of x and y. And in the first example here, suppose we invest half in x and half in y. So we can easily calculate the expected return in that case, 9%, 10 and 8, weighted average, easy. We can calculate the variance, which is again nothing else than setting in the values in the formula, 4.57%. But obviously we can also do that for other combinations, not only 50-50. We can have everything in x, 75% in x, 50 as here, 25 or nothing. And again, this also shows just some possibilities. You could also have 75.8%. There is an unlimited number of possibilities. So now, if you look at these portfolios that consist of x and y, I think there is one thing that's really striking. If you look at these portfolio combinations, and if you look carefully, it should become clear that some of these combinations are very stupid investment ideas. So which combinations would you never do? Which are the bad ones? Stupid ones? Yeah? The last line, right? The last line seems pretty stupid because the last line is all in y. Okay? That gives you 8% return for 841 risk. But if you add a little bit of x, what happens is that your expected return goes up and your risk goes down. I mean, why wouldn't you do that? So risk-averse investors, and this is the most likely description of real-life investors, would always do that. And even further, if you add now more x to your y, so you add another chunk of x, so you go up 50x, what happens is that you go from 8.5 to 9%, and your risk further goes down. So even the second last row, that's a bad investment, right? You wouldn't do that. So now what happens if we add even more x? Well, if we add even more x, we again get a higher expected return, but now also risk goes up. The same for lines 2 and 1, higher expected return but for higher risk. So for lines 1 to 3, we are actually not totally sure which one we prefer. Right? And we will later today or probably next week see that this will depend on the level of risk aversion, how risk averse you are. Right? But what we already clearly see is that the last two rows are very bad investment decisions. We say that they are dominated by other portfolios. Because other portfolios offer higher expected return for the same or even a lower in that case level. Okay? So, I think this result so far is quite nice because we have really done nothing too complicated. Just very portfolio, very basic math and very basic thinking about portfolios. But we have already achieved something that we wouldn't have known without that. Without that, if you only look at X and Y, the two assets by themselves, none is dominated by the other. Because if you only look at X, 100% X and 100% Y, I mean, X has higher expected return than Y, but X also has a higher risk. So if you only look at the assets themselves, it could be that you think, well, Y could be a good investment decision. If you're very risk averse, you say, oh, I really cannot tolerate 8.72, I prefer 8.41, so you would invest in Y. But now that we have done this portfolio statistics and looked at the portfolio combinations, we have realized that only Y is a bad choice. Okay? Combining Y and X gives us an opportunity to actually reduce the risk by at the same time increasing the expected return, which is, I think, a quite powerful result so far. Good. Yeah.
I'm wondering for like ETF, we have many underlying assets. Right?
Yes.
So do we consider it as like a portfolio and we use the underlying asset to calculate, or we just take the price of the ETF and also the cost variance?
No, I mean, yeah, that's a good point. In reality, things can become very complicated. We will talk about that because you have literally an infinite possibility of combination, right? You can do both. I mean, you can use the asset and the ETF as an asset, or you use the individual stocks as an asset. Conceptually, you don't need to consider the ETF because it's just a specific combination of the underlying assets. So conceptually, if you want to calculate all possible investment opportunities, you just forget about the ETF and you calculate all the different combinations of the different stocks. Okay? Because the ETF is doing nothing else for a specific combination. And if you do that, you would end up with millions or billions of specific combinations, and single points in that would be the ETFs. Okay? But we will see. That's impossible to do, so that's why people have found a shortcut. Okay, but that's like 2 lectures ahead. Other questions? Okay, then let's have the first break now, 10 minutes. Okay. So, second part for today. So, we already kind of made some achievements. We found out that some portfolio combinations are actually not great. Yeah, pretty bad. And a lot of everything we did so far relied on the assumption of normality. Okay? So I want to come back now to this assumption and ask a little bit further what happens if returns are not normally distributed. And then I want to show you some empirical evidence on whether returns are normally distributed or not. So what is if returns are not normally distributed? Well, then standard deviation is no longer a complete measure of risk. So we would need to consider higher order moments to accurately describe the dispersion of the distribution. So it's a very crucial assumption. And this assumption of normality allows us to ignore skewness and kurtosis. If the returns would not be normally distributed, we would need to consider their skewness and kurtosis in addition to the measure of location and the measure of dispersion. So these are the third and the fourth order moments. The skewness measures the asymmetry of the distribution. So whether the distribution is tilted to the left or to the right. If you look at that, this is the skewness. The distribution can be symmetric or it can be left or right tilted. Okay, so that's the skewness. That's what the skewness measures. The good news here is that the skewness is not a big issue because returns seem to be relatively symmetric. I'll show you in a second. The other moment that we could consider, or that we would need to consider if returns are not normally distributed, is kurtosis. And kurtosis measures the degree of fat heads, or how many observations we have at the extreme ends of the distribution. Okay? So in gray here, what you see is a normal distribution, and in blue we have a fat-tailed distribution. So both can have the same expected value, and both can also have the same variance. But the blue one has a higher kurtosis, an excess kurtosis. So the kurtosis of the normal distribution is 3. So if this one has an excess kurtosis of 3.35, or an excess of 0.35, the difference is 3. If we have a fat-tailed distribution, what that means again is that we have more observations at the extreme ends of the distribution. So events like minus 50% return, those events would be super rare under normal distribution, but under a fat-tailed distribution, those events would occur from time to time. Okay? This is not only true for extreme negative events, but also for extreme positive events. So fat-tailed distributions simply have more extreme positive and extreme negative events. So, skewness, kurtosis, asymmetry, fat-tailed. If we look at the empirical evidence, and people have looked at that for the last 50 years at least, 60 years, 70 years, there is no completely final answer to the question whether returns are normally distributed. But we have a pretty good understanding of the mistakes that we make if we assume normality. It's not perfect. Returns are not exactly normally distributed. But it's also not terrible. And it will depend a lot on the setting, whether it's reasonable or not. So there is a statement from the website of Eugene Farmer and Kenneth French that I think summarizes what we know quite well. So this is Eugene Farmer. You will see him several times in this lecture. He is one of the fathers of modern finance and asset pricing. He got this kind of Nobel Prize not too long ago. And this is Kenneth French, who is a researcher who did a lot of work together with Eugene Farmer. Okay? So what they say is that distributions of daily and monthly stock returns are rather symmetric about their means, indicating that skewness is not an issue. It's relatively symmetric. But the tails are fatter than would be expected with normal distribution. So, symmetric, but fat tails. And this existence of fat tails is actually interesting. This is not something that is like newly discovered. This goes back to work, among others, by Eugene Palmer himself, from the 60s. So even in the 60s, people found that there are fat tails. And the normal distribution is not really accurate, especially at the tails. Okay? Yeah, so this is from your textbook. Despite the issues raised by the financial crisis, we find no strong evidence that the normal distribution fails to describe portfolio return. There is some evidence of greater exposure to extreme negative outcomes. So again, that fails. So I think this is kind of nice what our textbook here does, so that's why I took a picture. What this is for different asset classes, treasury bills, T-bonds, gold stocks, large US stocks. They looked at historical returns over the last 9 years or so, from 1926 to 2009. Okay? So they look at historical returns and plot them into these bins. So these bins is the historical distribution of the returns. The higher the bin, the more returns are in that bin. Simply using historical data of the past 90 years. And then in blue, they try to fit a normal distribution into that. And then they want to see how well the normal distribution, how accurately the normal distribution describes this black bin. And if you look at it, I mean, it's not perfect, of course. There is noise, there is measurement error, but the normal distribution seems to relatively okay-ish describe the historical returns. So it's not terrible. So that most of the returns, most of the distribution here, seems quite accurate. The biggest issue we really have with this normality assumption are the fat tails. There is now a lot of evidence that fat tails exist. And this is problematic in some settings because if you assume normality again, you have this blue distribution. But if in reality the returns are distributed with fat tails as this green distribution, the blue distribution super substantially underestimates the probability of large negative or large positive returns. So, this is good or bad? What does this mean for us? For us, there is a good news, and this is that most of the returns seem to be relatively accurately described by the normal distribution. So in our setting, we really focus on the overall distribution, and we are not specifically focusing on the tails. Right? I mean, for portfolio selection, we really focus on the overall distribution, and not specifically at extremely positive or extremely negative events. So in the context of portfolio theory, portfolio selection, it seems quite reasonable to assume normality. It's not a bad approximation. However, if you do something like risk management, actually what you are only, the thing you're really interested in is here, large negative events. If it's risk management, you want to know, can my bank survive that? Or how much money should I keep as liquidity reserve to be able to withstand the next crisis? So if you do such things and you assume normality, I mean, that's nonsense, right? Because then you explicitly want to capture those negative events, those large negative events. So if you do risk management, you must never ever assume normality. That's complete nonsense. If you do portfolio theory, it seems quite reasonable. And that's what I said at the beginning. Returns do not exactly follow normal distribution. But in some settings like ours, it seems a reasonable approximation. In other settings like risk management, no way. Okay? And it's actually interesting that after the financial crisis, people found out that until the financial crisis, a lot of banks, even bigger banks, they used very simple risk management tools. And very often what they did is they assumed normality. So they dramatically underestimated their risk. And this is not the factor that caused the financial crisis, but this is one factor that contributed to the financial crisis. The underestimation of risk by banks because they just assumed the wrong distribution. So for them, back then there was this saying that something like the financial crisis that can only happen once every 200 years, according to the models that they had. But in reality, we know that those negative crash events, they happen once every 2 to 3 decades or so. So much more frequently than every 200 years. And that's really because they dramatically underestimated the probability for such events because they used the wrong probability.
To be conservative, should we lower our the gain estimates and also increase the variance estimates?
Yeah. So like the cheap fix, it's not a fix, but a simple way to account for the fact would be that if you calculate things under the normality assumption, you say, look, I use normality assumption, I know I underestimate extreme loss events. So basically, you increase the variance. By how much? That's a difficult question. Not easy to say. But yeah, it's something that you could consider. Of course, I mean, if you are a bank and you do risk management, you shouldn't start with the normality assumption. You should start with more accurate distributions, which makes things mathematically much more complex, but it's still doable. Not for us, because that would be beyond the scope of a class, but if you have computer systems and stuff, I mean, it's not difficult conceptually to use more complex mathematical distributions. Okay? Good. So, let's talk a bit about practice here. So, how should we now actually fill this table? Right? I mean, remember, now we talked a lot about this table, about the distribution assumption and all those things, but we still actually don't really know how we should bring the numbers into that table. And the truth is, we are actually interested in one thing, but we are doing another thing. So what we are interested in is the future probability distributions. Right? So every row in this table should be a future state of the world and the return in that state of the world. But because it's so difficult to come up with that, to create that, what people usually do is they use past realizations to fill that table. So every row in the table would be a past return, and that would be equally weighted. So this is by far the most common approach. Okay?
How far should we look back?
I'll come back to that. Okay? So, the really big advantage of this approach is that it is very simple. And you can go Google Finance, Yahoo Finance, Bloomberg, S&P, Thomson Reuters, whatever you like, and download historical data, and then you fill your table, you can calculate expected return, variances, covariances, very simple. The problem is that this is not actually what we want conceptually, because what we want is future probability distributions. So the assumptions that we need to make here, the core assumption that we need to make here is that the past returns are drawn from the same probability distribution as the future returns. Or in other words, that the underlying true probability distribution does not change over time. Think about it as there is a data generating process, or a process that generates this data, and this process always draws from the same distribution. If that's the case, then it's perfectly fine to use historical data, because then historical data will actually accurately capture the actual distribution. The problem is, if this data generating process, if the actual distribution changes over time. Because then we use data from a time period when the distribution was different than it will be in the future. Okay? So that's the problem. We need to make this assumption that the probability distribution did not change over time. That's the problem. The advantage is it's very simple. There are some alternatives to this very simple approach, but I will show you in a second that they also have problems. Let me postpone that for a second. So if you do this historical approach, I mean, things are super simple. I mean, then the return, the expected return is just the arithmetic average of the past returns. The variance, I mean, you can easily calculate that. It's like super simple. For the variance, the only thing we have to keep in mind is that we have to make this n-1 adjustment. So this n-1 adjustment is called the Wessler's correction. And we have to do that because of something that is called the degrees of freedom bias. And I will not go into the details here because we just don't have time. You can Google that and look at your statistics book. I just want to give you the brief, super brief intuition. Okay? This is the formula 1 divided by n that you can use if you actually estimate the variance on the overall population, on all the data that exists. Then we use 1 divided by n. That is never the case actually in our settings. So in our settings, we always have a sample, a random sample of the true population, the full population. And if we use this random sample of the full population, we always have to make this n-1. Okay? Again, I'm not giving you the mathematical explanation, but an easy way to remember is, if you only use a sample instead of the full population, you have to punish yourself. And you have to make the variance a bit higher, because otherwise you would underestimate it. How do we make it higher? Well, we are not dividing by n, we are dividing by n-1. So that makes it a bit higher, and that counters this degree of freedom bias. Okay? So this is really not core for this course. If you're interested, look at your statistics books. There will be a lot of explanation of that. We just have to remember, if we do it, n by n-1. So, let me spend more time on this practical considerations. So this is actually going back to your question, how long should the time series be that we There's a trade-off, as always, or as often. If you use a longer time series, you draw more data from the probability distribution. So actually, your random sample will get closer to the true population, and there will be less noise and less estimation error. When you estimate the variance, when you estimate the expected return, right? The more data you draw, the closer you get to the true population, and the lower your error will be. So, extreme case, you only draw one observation. I mean, there is no way you can calculate the variance and the mean with one observation. That's just not enough. So you need a lot of data actually to approximate the actual distribution. So from that perspective, we want to use a lot of data. However, if we use a lot of data, we have to go back long time in history, and this assumption that the true probability, underlying probability distribution did not change over time becomes harder to justify, right? I mean, if you go back 100 years, it's pretty hard to argue that the underlying probability distribution of a company 100 years ago was the same as it is today. That's the trade-off. This assumption that the probability distribution did not change, which we always need, is easier to justify if you use a short time series. But if you use a short time series, you get more estimation noise and estimation error. So we need to balance those two things. So, what is typically done is something like probably 5 years, 10 years. Those are this is a rough estimate of what people use. 5 years, 10 years, probably a bit more, probably a no, not probably, less is already a bit critical, but probably a bit more. You always have to think about the reasons why you're doing it, why you're not using more data. You're not using more data, more time series, because you are afraid that the underlying probability distribution changes. Right? Now, like also for your project, if you do something like that, you have to know your industry. If the industry is relatively stable over time, it might be okay to use 30 years or 40 years of data. But if the industry is fast changing, very rapid, very dynamic, probably 5 years would be more accurate. I mean, think about Apple. I mean, Apple constantly changes itself. It started as a computer manufacturer, then it was basically a phone producer, now it's a full-service IT provider, or how to describe what Apple is actually doing. But it's changing very rapidly. So in such a situation, we shouldn't use data from the 1980s for Apple. Okay?
I'm wondering, should we also use like data from other firms, like similar firms, like the application of Google or Samsung?
So if you look at a specific stock, you would only use data from that stock. Okay, you wouldn't use data from other stocks. Because there is no way to justify that both have the same underlying probability distribution. You use data from other firms, and what you're probably thinking about is valuation, where you do peer valuation based on peers, multiples valuation, for example. There you would use data from other firms, but not for an exercise like this. So you will only use the firm itself. Okay? And sometimes, and that is also why it's really important to know your industry, you do have some structural breaks. Think about deregulation. So an industry could be regulated until some time, and then suddenly it becomes deregulated. Like in many parts of the world, this happens with electricity generation. So obviously, before and after deregulation, these firms were very different. So if that happened in your industry, you should only use data from after the deregulation, not from before the deregulation. Because that would be very hard to justify that the probability distribution does not change if you have such dramatic events. Okay? So, again, it's really kind of the trade-off. You have to be aware of the trade-off. Generally, we can say 5 to 10 years, but it's possible to make adjustment for industries. So, if historical data is not great, and it isn't, right? Because we have to make the strong assumption that the distribution didn't change. Why don't we simply use something else?
If you're assuming something is like similar, that we break it up like 5 years, and compare whether there's anything different inside data, so that we can know if the past has changed quite a lot. Because if break it up and then literally where is it?
You could do that. I mean, conceptually, you wouldn't gain too much, because if you find it's very different, I mean, that could be because of two things. First, it could be that actually the true underlying probability distribution changed, or you just have a lot of noise. So you still cannot really get rid of this core problem. But it's a good idea. Yeah, so for your project, I really encourage you to do things like that and show that you understand the problem. Not everything has to be perfect, right? I mean, even analysts in real life, they do many things that are far away from perfect. So, but yeah, if you have such ideas, feel free to incorporate that. Okay, so the idea is good. Yeah, if you don't like historical data, why don't we just use something else? And the short answer is there is no good alternative. Because also the alternatives that we have are problem. So, what is again the problem we want to build this table? Right? So instead of using historical data, what we could do is we could just approach industry experts, industry insiders, and ask them for their help. Say, look, Tesla, BMW, come up with a table, 20 rows, each row a different state, and then you give us your expert opinion on the return in that state. We could do that. And it's partly done in reality. Yeah? The problem of this approach is really it's slow, it's expensive, and probably the worst, it is very interesting. Because if you do that, and if you go to one industry expert, he will come up with two things. You go to another industry expert, he will come up with two different things. So if I now look at what you did in your analyst report, let's say, and I want to replicate your findings, I mean, there will be no way, because if I ask a third industry expert, the third industry expert will come up with a third paper. They will all be slightly different. So it's actually quite intransparent. Okay? If you use historical data and you come up with an expected return of 5% and a risk of 20%, I mean, I can easily download the past realizations and calculate that by myself, and I can see why if you made a mistake, for example. So, industry experts, a possibility, but slow, expensive, not transparent.
We want to look at past results of the industrial research or insider collector. If the past they do a terrible job, then but it will go back.
But this goes back to this intransparency. I mean, there is no database of who did a good job and who did a bad job, and it's not easy. But of course, I mean, you could. But these are the core problems. So what people then sometimes do is they combine historical data with estimations from experts. So for example, you could say that, let's say you had such a structural break like deregulation. So then you use historical data to estimate things, and then you ask the industry expert if he thinks that you should adjust the variance or the expected return because of recent developments in the industry. Yeah? So then you could say, for example, yeah, the industry experts recommends that you increase the variance a bit because recently this industry became more volatile. Or there have been other very recent developments that are not yet reflected in historic data, obviously, so we should decrease the estimated return a little bit. Okay? So that is possible. Again, kind of same problems as the experts alone, slow, expensive, not very transparent. But it's possible. Yeah? I mean, there are also other ways. Probably the theoretically nicest way to estimate future variances is to use options, data from options, and so-called option-implied volatilities. So the option-implied volatility is very simple. You have an option and you have the price that you can observe in the market, and we know how the option is priced. We know the pricing formula, the Black-Scholes-Merton model. So we can solve the Black-Scholes-Merton formula for the volatility, which is one component in the formula, and then set in all the values, including the current market price, and then we know which volatility the market participants assume that they price this off. So that is conceptually quite nice because it's forward-looking. The problem here again is it's often hard to do in practice because you need liquid option market for the stock. And not so many stocks have liquid option markets. And even if you have liquid option markets, the option price data is often more difficult to obtain than just stock price data. Long story short, there are some alternatives for using historical data. None of them is perfect. In practice, 99% of the time people use historical data. Yeah? Good. So when we talk about measuring returns, so one thing that I want to briefly, but this is really briefly, this is not core here, briefly want to mention is the difference between nominal and real rates. So most of the time, this is what you should remember, when people measure returns, they use nominal. They are not using real rate. What is the real rate? Well, the real rate is approximately the nominal rate minus the inflation rate. Okay? approximately here, because if this is discrete time, we have to consider this compounding effect. If it's continuous time, it's exactly the real rate, it's exactly nominal rate minus inflation. What I want to show you, because I think it's kind of interesting, it fits to that topic, is historically, if you invested, there is a huge difference between looking at historical nominal rates and historical real rates. Okay? If you invested $1 in 1926 in treasury bills, so presumably, we assume it's relatively risk-free, right? So 1926, and you kept that investment until 2050, then your $1 grew to $20.52. So it seems like an extreme increase at $1 to $20. But most of that increase over that 90-year period was driven by inflation. Because if you look at the real terms, the $1 only grew to $1.55. Over these long time periods, there's really a big difference between nominal rates of return and real rates of return. And actually, if you look at treasury bills, so this is this time period from 26 to 50, if you look at treasury bill rates all month, 3.46% on average, inflation 3%. So treasury bills approximately compensated over the last 90 years the whole of for inflation. But that's it, not more. The real rate was very close to zero. And in the first half of their sample, actually the real rate was negative. In the second half, the real rate was positive, but also not super high. So if you see something like, sometimes you read about, yeah, you invested $1 in 1950 and then it's grown to whatever. Yeah, even if you invest in something risky, it has grown to $20, but mostly because of inflation and not because your purchasing power increased so much over that time period. So that's also why part of the reason why treasury bills compensate you for inflation, and why this is approximately really exactly their return, why this is approximately the return that they get, is that the nominal rate of a bond consists of multiple parts. One is the real rate and one is inflation forecast. The real rate actually compensates the holder of the bond for different risks that the holder takes, like default risk, liquidity risk, maturity risk, different risk factors, not so important now. All these risk factors, if you think about treasury bills, they are actually non-existent. There is no default risk, there is no liquidity risk because this is a super liquid market. There is no maturity risk because it's really very short term. All these risks are very small. So actually the real rate, the nominal rate, equals approximately the inflation forecast. Because the real rate should also conceptually be very close to zero. So this is the so-called Fisher reflection. But this is just a small piece of additional information, not super relevant. I just want to highlight that it's conceptually a quite big difference if we measure returns in nominal or in real. Most of the time, also for your project, you do not do inflation. You just do yeah, there is an interesting phenomenon that's not this here. That actually, even if the treasury bill exactly compensates you for inflation, typically investors lose because of taxes. So let's say the real rate, the nominal rate is 10%. Yeah? And the inflation forecast is 10%. So the real rate is 0. Right? But that's not exactly true, because the real rate after tax would be negative. Because the tax authorities, typically they look at your nominal rate of return, and then they calculate your taxes based on the nominal rate of return. So actually you have 10% nominal rate of return, which means you have to pay tax on this 10% return, which makes your real return actually negative. So this is a pretty strange phenomenon, because if you change this example to a case where you have zero nominal rate of return and zero inflation, there is no tax anymore, but you also have zero real rate of return. So in economic terms, 10% nominal and 10% inflation, and 0% nominal and 0% inflation, it's the same thing. It always gives you 0% real return. But in reality, it's not, because of taxes. It's not very, economically, it's not very easy to justify why we tax nominal rates of return, or nominal returns, and not real returns. So economically, it would be more justifiable, clearer, if we would tax real returns, not nominal returns.
It would be much more complicated.
Sure. The problem is it's much more complicated.
Everyone's real weight might be different due to their consumption pattern.
No, I mean, what we could do is we could just say, look, the inflation rate was 3% in a year. So every interest rate below 3% is not taxed. So we start taxing interest above 3%.
Different consumption patterns, the 3% might not be.
Sure, but it would still be closer to what is economically meaningful than to just assume that the inflation rate is zero. I agree. I mean, if you want to do it very precisely, you would have to calculate a different inflation rate for everybody, but that is of course not possible. But you could use the average inflation rate and subtract the average inflation rate from the nominal interest that you get, and then tax the real.
But then, isn't it the real case would be really increase the tax rate while providing something like this, because it's not the real or nominal tax return will be lower once the change is there.
Yeah, sure. I mean, probably the tax authorities would then just increase the tax, and it would be the same thing. I'm not saying that this would be better for the people or something like that. I mean, that's from an economic perspective not interesting. I have a very strong standpoint on that.
Because if you tell people we're going to increase taxes, people are not going to get that.
Sure. But what I'm saying is that from an economic point of view, it's not easy to justify why we tax nominal interest rates instead of real interest rates. All right. That's it. The first subchapter. Now let's talk a bit about portfolio selection. Risk aversion, capital allocation to risky assets. So we will assume throughout this whole chapter that we have a risk averse investor, and the risk averse investor faces a problem. And the problem is he has to split his wealth between a risky asset and a risk-free asset. Well, in this very simple world, we will only have these two assets, a risky asset and a risk-free asset. There will be nothing else. Okay, nothing else, only risky and risk-free. But before we can then really answer the question how our investor can optimally split his wealth between risky and risk-free, we will need to develop some tools. And one of these tools is the so-called utility model. The utility model will help us to understand how attractive different risk-return combinations are for an investment. Okay. So before we do that, this is just a small overview on the differences actually between speculation and investment. And what we should highlight is that information actually plays a critical role when we make investment decisions, but not necessarily when we do gambling. Okay? So what is speculation or investing? Well, this is taking risk because you expect a gain. Yeah? So typically, if you do investing, the two parties that engage in a transaction, they have different beliefs about the future. So let's say, very simple example, you purchase today one stock of Microsoft. versus that on the secondary market. So you want to buy, and you buy it from somebody who wants to sell. So you think that the stock is undervalued. Sorry. So you think that the stock is undervalued. You want to buy. But somebody else thinks that the stock is overvalued. So they are actually selling. So there are different expectations about the future of the stock. So this is what we call investing or speculation. There is also gambling. And gambling differs from this in a very simple way. If we do gambling, we basically assign the same probabilities to the different outcomes. Okay, so example, I roll a dice. And I play with you a little game. If the dice shows 1, 2, or 3, you pay me $100. If the dice shows 4, 5, and 6, I pay you $100. So rationally, we know that the probability for each outcome, unless I cheat and manipulate the dice, is 50%. Right? There can be no disagreement about that. So that's very different to buying or selling a stock where you have disagreement or different beliefs about the future. So gambling is typically always when you assign the same probability to the possible outcomes. Speculation, different probability. This is just an example. There were two investors, Paul and Mary, and they disagree about the future US dollar exchange rate. So Paul thinks it will be high and Mary thinks it will be low, so they bet. So whoever wins gets $100. So if they assign different probabilities, which seems to be the case here, this is speculation. If they both would assign the same probability of 50-50, that would be gambling. But in the case of investment, we are mostly talking about possibility 2, different probabilities, because Paul thinks it will be high and Mary thinks it will be low. Okay? Of course, in reality, if you want to distinguish different forms of risky choices, if you want to classify them between gambling and investing, there is some gray. I mean, it's not only exactly gambling, exactly investing. So fixed income equities, that's typically investing because people have different beliefs about the future, and that kind of is the reason why they trade. Yeah? But we also have other things that are gambling, like lotto or blackjack. That's typically more gambling because there is little disagreement about the probabilities if you do lotto or blackjack. But then you have things in between, like poker. I mean, you could argue if you're a very skilled poker player, then you have control over the probabilities. Well, people, I guess, are pretty overconfident in that dimension, but probably they at least think that they are better, so they assign different probabilities, so it could be kind of investing, not only gambling. So the point here is it's not always totally true. There is something in between. So it's not super important, just like short overview on the difference between gambling and investing. This is more important, risk aversion and how do risk averse investors behave. Risk averse investors, which are basically our modern investors in our world, all our investors will be risk averse. Okay, understated. Otherwise, it will always be risk averse, the best investor. So they reject investments which are fair gains, risk premium of 0 over. What does that mean? A fair gain would be a game where you can win, for example, exactly nothing. If I generate a lottery and I tell you, look, with a probability of 50%, I give you $1,000. With a probability of 50%, you give me $1,000. The expected value of that is 0. 0.5 times 1,000 plus 0.5 times minus 1,000. And the risk premium is actually 0. Okay? So this is exactly a fair game. There is no risk premium. And the risk averse investor would always reject it. The risk-averse investor will always say, no, I don't want to play that game. Yeah? But the risk-averse investor does not reject all risk. The risk-averse investor also is willing to consider risky positions if there is a positive risk premium. So if I will now change this lottery and tell you, look, with a probability of 50%, I give you $2,000. And with a probability of 50%, you lose $1,000. I mean, now suddenly, we have a positive risk premium.
When we talk about like the return, do we look at just the nominal or the real rate? Because if you look at the real rate with inflation, then if you put some money into some investment, then probably when it comes out, it's the
Yeah, we look at nominal. This is only nominal. Right now in our model world, that plays no huge role because our model world will be a one-period world, so very short. There is no inflation in our model world. In the real world, I agree. I mean, it's a more tricky question. We probably have some time to talk about that later. So the point I want to make here now is that the risk-averse investor considers the risk-free asset and risky assets, lottery, for example, that have a positive expected value, a positive risk-free. Okay? And I will show you some of these lotteries on the next slide. The portfolio attractiveness for this risk-averse investor actually increases with expected return. This makes sense, right? I want higher expected return. And the attractiveness decreases with risk. It also makes sense. The risk-averse investor doesn't like risk. Okay? The tricky part is really if you have different. Let me go back a few slides. So this table here. This is exactly why the last row and the second last row are bad, right? I mean, the risk-averse investor dislikes that because he can have higher return for lower risk. The more tricky part is really the first three rows. I mean, how can we now decide whether the investor prefers row 3, 2, or 1? That's more tricky, and that's why we need to introduce this utility function. Okay, so the utility function will assign to every risk-return combination a utility score. Yeah. So, but before we do that, and before the break, let's do a few small lottery games to understand probably a bit further more what I mean by this risk aversion. Okay? So, this is a game. Yeah? You have to choose. You want to play a lottery with me, or you want to just take the sure game. So the sure game is $100, and I can give that to you now. Actually, I don't, but in the game, I would, which I don't, but I would. So you get $100 from me, or you play a lottery with me. In the lottery, you have 90% chance of winning nothing and a 10% chance of winning $500. Who wants to play the lottery? One. Good. Who wants to take the 100? So most of us seem relatively risk averse, but some are more risk loving, which is perfectly in line with what we see in reality actually. So here, the expected return of the lottery is $50. Yeah? So actually the risk premium is negative. What you get here is an expected return, of course, of $100, here an expected return of 50, so you have a negative risk premium. So our risk-averse investor would always say, I take the sure game, because there is no reward in terms of higher expected return for paying the lottery. Yeah? The reward is in terms of higher expected return, of course not in terms of higher realized return, because there is uncertainty. Now I'm changing the lottery, so now you will still have the opportunity to take 100 picks, or you have a 10% chance of winning 1,000 and a 90% chance of winning nothing. Now if you reevaluate your choice, I guess some of you will now take the lottery. It seems more attractive. Suddenly we get 1,000 with a 10% chance, not too bad. So the expected value here is, of course, 100, the expected value of the lottery, and the expected value of the true gain is again. So the risk premium here is, what's the risk premium? 0. Right, the difference between the sure option and the risky option is exactly 0. So our risk-averse investor, what would she do? Sure gain. She would still not play the lottery because there is no reward. The reward is 0. Yeah, and then I can tweak it again, so now we suddenly have a 10% chance of winning 1,500. You take the lottery.
Can we pool?
No. I'm the quiz master, you cannot fool. So, now if you think about it, I guess really, I mean, it's hard to say something like that in a hypothetical setting, but I guess many of you would now probably take the lottery. So why is this completely in line with what we say? Because, or what we assume here, because now the lottery has an expected value of $150. The sure gain is only $100. So now suddenly the risk premium is $50. And now even the risk-averse investors, they would consider the lottery. If they really play the lottery or if they still take the sure gain, that will depend on how risk-averse they are. So not all risk-averse investors will automatically play the lottery, but they will consider it. And some risk-averse investors will play the lottery. Some might still take the sure gain because they are just very risk-averse. They have a very high level of risk aversion, so they might still take the sure gain. Okay? So this is kind of what I mean with risk aversion and risk premium. Okay? Good. Sorry. So, time for the second break, 10 minutes. Okay. Okay, so last part for today. So now that we have a bit of a better understanding about risk aversion, let us take what we now learned to an example that is closer to investment. Okay? So this example consists of 3 portfolios, portfolio L, M, and H, low, medium, and high risk. They have expected returns of 7, 9, 13%, and risks of 5, 10, and 20. Okay? So now we want to understand which portfolio an investor would like most, which one he prefers. Okay? Unfortunately, in this example, it's not the case that one portfolio would dominate another portfolio, right? Because for all portfolios, if we increase expected return, we also increase risk. There is no portfolio that is an obvious choice. If there is no portfolio that is an obvious choice, we need to rely on something that is called a utility function. The utility function will result in a utility score, and this utility score captures the investor-specific risk-return trade-off. So in other words, we will define a function, and this function will assign to every risk-return combination an investor-specific utility value. Okay? So one very commonly applied utility function is this. The utility equals the expected return minus half times A, and A is the coefficient of risk aversion times risk measured by variance. Okay? So this is one commonly applied utility function. It is not the only one. Okay? So there are some reasons why we use that one, mostly because it's simple. But I want you to understand that this is A, not the only one, and B, this is just defined. I mean, there is no way we can know that this is the correct utility function. In a couple of slides, I will actually say or show you some evidence that these utility functions suffer from several problems. Okay? But they are still useful for our purpose. So for now, let's assume that we can assign a utility score to every risk-return combination. Okay? So what is the utility? Well, the utility increases with expected return, which makes sense. And the utility decreases with risk, which also makes sense, as long as A is positive. So if A, the coefficient of risk aversion, is a positive number, the utility decreases with risk. If we have an investor who doesn't care about risk, the so-called risk-neutral investor, the level of risk aversion, the coefficient of risk aversion would be 0, and the utility would only depend on the expected return. Because this term cancels out. This term goes away. If A equals 0. And the most extreme case is the risk-loving investor. For the risk-loving investor, we would have a negative A, a negative coefficient of risk aversion, and for this investor, the utility would actually increase with risk. Because this investor likes the thrill of the risk, so for this investor, the utility is higher if there is warrants. Okay? But these are not the standard cases. In our standard case, we will have a risk-averse investor, and the level of risk aversion will be captured by A. Some investors are more risk averse, then A is high. Other investors are less risk averse, then A is low. For all investors, independently of their level of risk aversion, the utility of the risk-free asset is what? Utility of the risk-free asset is always the return of the risk-free asset. Right? Because for the risk-free asset, risk is 0, so this term is gone. So the utility is only ER. And ER is the risk-free rate. Okay? So this doesn't depend on the risk aversion. Risk-free asset always RM or ER. Yes?
We need to consider when risk-free asset requires us to lock in that amount of asset, so it's not that liquid.
No, that we don't consider. This is really, it's a very simple world, there is no liquidity constraint and nothing like that. Okay? So what we can do now is we can introduce 3 investors, which are named 1, 2, and 3, and all of them have a different level of risk aversion. Okay, so all of them have a different level of risk aversion. So investor 1 has a risk aversion coefficient of 2, then we have 3.5 for investor 2 and 5 for investor 3. And now we can calculate the utility score for all portfolios and all investors. We have 3 investors, 3 portfolios, so we have 3 times 3, 9 utility scores. Because keep in mind, the utility score is investor specific because A is investor specific. Okay? So if we do that, we find that the first investor has a utility of 0.0675 for the L portfolio, 0.08 for the M portfolio, and 0.09 for the H portfolio. How did we do that? Well, really simply setting in the values in the utility formula.
Would it be possible that a mixture of that portfolio was of a higher score?
That would be possible, but that is not an option. So in this option, in this example, we only have 3 investment trusts. Okay, but you're right, and we will see that at the very end of today, combinations could be better. Yeah. For our first investor, she has the highest utility if she invests in portfolio H, 0.09 higher than M and higher than N. For investors 2 and 3, they are more risk averse, so they penalize risk more severely, so they get the highest utility if they invest in portfolio N. Okay? And for all of them, portfolio M or H, so the risky option, the risky portfolios, are more attractive than the risk-free asset because the risk-free rate in this example is 0.05. So the utility of the risk-free asset is 0.05, which is lower than the utility of these risky portfolios. So even though these investors are risk averse, that doesn't mean they do not invest. That does not mean they do not invest in the risky portfolio. If they give them a higher utility, there is a positive reward for taking the risk, they might very well invest in the risky portfolio. Good. So sometimes students want to know what the utility actually means. So what does it mean to have a utility of 0.09? What is the intuition of that? And honestly, there is no very dramatic intuition behind that. It's just a score. But if you want to have some intuition, this is actually the risk-free rate that you would have to offer this investor so that this investor is indifferent between this choice and the risk-free rate. So if the utility is 0.09, this means that this investment is equally attractive for this investor as a risk-free rate of 9%. If you want to have some intuition or some way to verbalize what the utility score means, I mean, this would be it. Equally attractive than a risk-free rate of 9%, equally attractive than a risk-free rate of 6.5%. Good. So, for risk-averse investors, the risk premium is negative or 0. They would never consider. So in that case, the utility of the risky portfolio is always below the risky asset. For the risk-neutral investor, I mean, this guy only charges an investment based on expected returns, right? They don't look at the risk. They don't care. And the risk-loving investors, they have a negative risk aversion. Actually, they have fun of risk, and they would accept fair gain. So if I would offer a fair gain, again, lottery, you lose $100 to 50% probability, you win $100 to 50% probability, is a fair gain. Expected value of 0. The risk-neutral investor would be indifferent. The risk-averse investor would say no. The risk-loving investor would say yes.
Are there some data on like the trend or different behaviors, like different types of investment, risk aversion or
yeah, I mean,
or lottery?
We will come back. We will get to that later in the lecture. But it's pretty obvious, right? If there's a positive risk premium in terms of higher expected return, people who have a higher risk tolerance or lower risk aversion, they will get higher expected return.
But what people that are risk lottery, like gambling their money on options and this all that?
It doesn't. It depends. It also depends on the instrument in which you invest, of course. If you follow the optimal investment strategies according to market risk portfolio selection model, actually the less risk averse you are, the more you would get on average in terms of expected return. Of course, not necessarily in terms of realized return, but your expected return, we will see that, will go up the more you invest in the risky asset, and the less you invest in the risk-free asset. Which makes sense, because if it wouldn't be the case, nobody would do it, because you need to offer a reward in terms of higher expected return for investing in the risky asset. Good. So before we move on, I want to make a 2-minute mental break here and say something that is probably not motivating, in the sense that what we do here is not very close to reality. The utility function that we use, this utility model, this goes back to the rational decision-making idea. Basically, it assumes that people are robots, and they make these decisions very rationally, always trading off risk and return in a certain way that we can put into a formula. Not very realistic. And in the last 30, 40 years, actually research has shown that people suffer from multiple biases if they make decisions. Okay? We ignore all of that. So in our little world, in our Markowitz portfolio model world, investors are robots. They have a risk aversion, and then they act exactly as we expect them to act according to their utility function. Is that realistic? No. But we need to start with that. We need to develop the models, and if we have time at the end, I will try to show you a bit how we can extend the models so that they become more realistic. Okay? So let me show you a few spotlights here on how people really behave. And this is one of the things that has been documented in the last 30, 40 years or so. This is the core result of a very famous theory that is called the prospect theory, which was developed by Danny Kahneman and Karl Tversky. And this is loss aversion. People are very averse to losses. So what this basically shows is here is utility in the vertical axis, and here on the horizontal axis is gains and losses. So if I give you $100, I give you $100, you gain $100, you become more happy. You get positive utility from that. The utility goes up. But if I take $100 away from you, your utility goes down by much more than it goes up if I give you $100. So the way how Kahneman expresses this is people hate losing much more than they like winning. Loss aversion, asymmetric reaction of people to gains and losses.
I think some companies do a lot of using this thinking by giving bonus ahead and then take it back if you.
Yeah, no, this is something, I mean, this was developed in the 70s and 80s, so this is well known. Companies use it a lot. I mean, this is the foundation of behavioral economics, basically. So the point here, why I'm mentioning this here, is really that we would ignore all these things in our rational utility model. It's just not possible to develop the core models of asset pricing with all these, considering all these biases. And it's perfectly fine to start from a simple model and later think about how actual biases or how actual behavior might change the results. But we should be aware of that. We should be aware that actually what we do is a simplification, pretty dramatic simplification actually. So these are the guys who developed prospect theory. This is Daniel Kahneman and this is Karl Tversky. So he did something else, or something related, but not exactly. Danny Kahneman received the Nobel Prize, which is not officially called Nobel Prize. It's called the Svergies Riksbank Prize in Economic Sciences in memory of Alfred Nobel, because Nobel didn't really donate money for an economics Nobel Prize. So you get a Nobel Prize for other disciplines, but not for economics, because these people say that he was not a big fan of economics. So then later, when they introduced this economics Nobel Prize, they couldn't call it Nobel Prize, so they used this kind of strange name. But that's important. So in 2002, actually, Danny Kahneman received the Nobel Prize for what he did in understanding human behavior under uncertainty and in advancing the knowledge away from this rational decision making into actual decision making, how people really behave under uncertainty. So he got it. Nearly all of his work was together with Carmen Tversky, but Tversky did not get the Nobel Prize. Why? Actually, for a sad reason, because he passed away before that. And the Nobel Prize, by its regulation, cannot be awarded to people who passed away. So they must be alive at the moment when the prize is awarded. So that's why only Danny Kahneman got it, but people know, I mean, that's their joint work. So, because I think this is something that we should be aware of, and it's also interesting. Let me show you a 1 and 2 minute video clip. This is an interview with Danny Kahneman on what he did and why he did what he did. So let's watch it.
Prospect theory, you can look at it narrowly and you can look. Prospect theory, you can look at it narrowly and you can look at it more broadly. So narrowly, it's a theory of how people make choices between gambles with monetary outcomes and specified probabilities. It's a very narrow field that it's supposed to account for. More broadly, it had some ideas that challenged the dominant model of the day, and those ideas made prospect theory more or less important as the foundation of behavior economics. There existed before us a theory of how people should behave, and we didn't touch it. That's called rational agent model. It's called expected utility theory. We didn't touch it. We just explored how people violate that theory and how they are different from what the theory says they should get things. What it allowed was it allowed us to see that people's attitudes to gains and losses are actually very different. And that is really the fundamental result of prospect theory. We call it loss aversion. And what it means is that people hate losing much more than they like winning. And we actually have a pretty good idea of the ratio, of the factor, by how much people hate losing more than they like winning. And it's about, on average, I mean, that's a crude estimate, but on average, it's between 2 and 3. So I'll give you an example. If you ask, say, Princeton students, how about a gamble where if it shows tails, you lose $10. If it shows heads, you win X dollars. What would X have to be before you like the gamble, before you're willing to take it? They'll want $25. You can do the same thing with their parents and talk of $1,000 or $10,000, and you'll get roughly the same ratio. So that's a very fundamental fact about people. Psychologists had a lovely phrase to describe it. He said that the emotional tail wags the rational dog. And so that is, there is a lot of that happening in today in psychology and in neuroeconomics.
Yeah. So we will not have time to really explore that further. I just want to give you a bit of an introduction to that and make clear that what we do is a simplification of reality. So how can we estimate risk aversion in practice? Well, actually, people use something like questionnaires. People confront individuals, often students, with risk, and then they look how they react, something like this. So you give students choices. You say, look, you have a probability you get 50%, $50 with certainty, or you play a lottery. What do you choose, A or B? And then they do this with a lot of students, a lot of different lotteries, and then they kind of back out the resources. Okay? It's of course not an exact science. So over time, we got a bit of a feeling of how the risk aversion varies across people. And the literature has also identified several characteristics, person-level characteristics that affect the risk aversion. If you want to read more about that, also the measurement of risk aversion, there's actually a nice website here by NYU, so you can take a look at that. What people found, researchers found, is that actually there are several characteristics that have a pretty strong predictive power for the risk aversion of people. So what do you guess? Which characteristics predict the risk aversion of people? Any ideas? What could be a factor that affects the risk aversion? Age.
Whether you have your family
Age, yeah.
composition.
Age, wealth, income, yeah. What else? Yeah, education, yes. Yeah, probably. That's not so much a person-level characteristic, but it has been shown that the same investment can make different choices across different investments. Gender is actually race probably too, yeah. I don't know about research on that, but I guess there is. So I guess there is an effect. Let me just show you a little bit. These are just some randomly chosen characteristics. This is gender. And actually, this is the amount that the students were willing to pay to avoid a lottery. So if this is high, this indicates a high level of risk aversion. So how much money in terms of expected return are the students willing to give up to avoid the lottery? And in this gray, in this light gray, these are female students, and in this dark gray, blackish, these are male students. And you see, it's slightly different. I mean, there is a lot of variety. So for both of them, both groups, there were some students who actually would be classified as risk loving because they have a negative risk premium. But female students tend to be, on average, more risk averse than their male students, on average. But both groups have quite a lot of variability. And for age, we have actually very strong evidence that age plays a huge role for risk aversion. So this picture is a bit, you have to be careful when you look at it, because this is basically risk tolerance. If this goes down, this means your risk aversion goes up. Okay? So the blue line shows risk aversion or risk tolerance over the life cycle, and you see that it clearly decreases with age. And in this orange, this shows short-term temporary fluctuation. Okay? But with age, people tend to become more risk averse. Okay? So this is really, if you think about investment decisions, and if you think about, let's say you are an investment advisor, this is really something that investment advisors use to make recommendations to their clients, because if they know that elderly people are on average more risk averse, they can incorporate that into their investment advice, right? If they know that the wealth is a huge predictor of your risk aversion, I mean, they will, and they do, they will propose different investments to wealthy clients and not so wealthy clients. So this is really the micro foundation why you do that, why that makes sense. Good. Now let's go back a bit, one step back, and think about our investment universe. So in this example, we plot risk and return. So this is risk, and this is expected return. So this way of showing risk and return, we will do that quite often. So expected return and risk. Yeah? So we have a portfolio P, and P has a specific expected return and a specific risk. Yeah? And then we divide the space here in 4 areas. Area 1, 2, 3, and 4. Yeah? Now, consider there is a risk, consider a risk-averse investor. Yeah? What can we say about all risk-return combinations in one relative to P? Are they more attractive, less attractive, equally attractive to the risk-averse investor? Yeah, all risk-return combinations here in area 1, they are more attractive to our risk-averse investor than P. Why? Well, because they have a lower risk and a higher expected return. Yeah. What about area 2? For area 2, we don't know, right? Because for area 2, what we do is we increase the risk, but also the expected return. So whether a specific point will be better or worse than P in area 2 will depend on how risk-averse the investor actually is. Right? How about area 3? Same thing, right? We get lower risk, but also lower expected return. And area 4 is pretty clear again. Area 4 is bad. Area 4 is bad because we get higher risk or lower expected return. Okay? So, now we want to understand, or we want to identify the points or the risk-return combinations in areas 2 and 3 that are equally attractive for our investor than P. And we can do that by drawing so-called indifference curves. So what the indifference curve actually is a line that connects risk-return combinations that are equally attractive for one specific investor. Okay? How can we find this indifference curve? Well, basically brute force. You take every risk-return combination, area 2 and 3, and you calculate the utility score for that, for the specific investor, and then you connect all of them with P that have the equal utility as P. Very simple. You can calculate all the utilities and all the investment opportunities in these areas, and then you connect those that have the same utility. That's how we can come up with this indifference. So all the risk-return combinations, all the points, and a point here is a risk-return combination. And conceptually, it really doesn't matter if that is a portfolio or an asset, that could be a commodity, a stock, a bond, a diversified portfolio, it doesn't matter. It's just a risk-return combination. So every point on this blue line has the same utility for our investor. Okay? That's how the indifference curve is defined. So our risk-averse investor would be indifferent between investing in P and investing in Q, for example. Okay? How would the indifference curve for a risk-neutral investor look like? Risk-neutral investor, how would the indifference curve look like? It's a straight line, okay? No. What is the slope of the straight line? The risk-neutral investor does not care about risk at all, right? So yes, it's a horizontal line. For the risk-neutral investor, it's only about expected return. So if the expected return is 5%, the utility would be the same for all levels of risk. So if he can get 5% with a risk of 20%, that gives the same utility to him than if he can get 5% with a risk of 0. So the indifference curve for a risk-neutral investor is a flat line. This is a risk-averse investor. How would the indifference curve for the risk-averse investor change if he suddenly becomes more risk-averse? Let's say he wakes up and realizes, oh, all my money was stolen. So now he's poor, so he's becoming more risk-averse. How would his indifference curve change? It would become steeper. Yeah. Risk-neutral, horizontal line. It's only about expected return. The expected return of, let's say this is 5%, delivers the same utility no matter how high the risk is. For risk-averse investors, their utility curves are upward sloping. Why? Well, because if risk goes up, they require higher expected returns so that they end up with the same utility. As I said, a risk-free asset has a utility of 5%. So now if I increase the risk, so to have a utility of 0.05 again, I must have higher expected return. So actually, it goes up. And if I increase the risk even more, it goes up even further. So to compensate for the higher risk, you need higher expected return to achieve the same utility. Because remember, these curves, all points on these curves, are risk-return combinations that offer the same utility to our investors. And that's also then clear why lower risk aversion is less deep, because if you increase risk and you are just a little bit risk averse, you do not require so much compensation in terms of higher expected return for that higher risk. But if you are more risk averse, you require more compensation in terms of higher expected return. And if you're even more risk averse, you require even more compensation. Our risk lover investor, again, it's not super common and super realistic, it's even downward sloping, because risk lover, if risk increases, he accepts a lower expected return to arrive at the same utility because he has this additional utility from the thrill of the risk. Right? So the risk lover gets some utility from the risk. So if risk goes up, the expected return can go down, so that he or she will have the same level of risk capital, the same level of utility. Clear?
But then wouldn't some risk level with that, like 100% of losing the money would give them a much higher?
No, that's not good. It's about expectations, right? It's not about realization. If they find something that is super risky, even if it has a negative return, they would conceptually do it because they like this risk so much. But I mean, think about people who are gambling. I mean, it's not so far away. On average, they lose. But they like the risk of gambling so much that they are willing to not even get no positive expected return, they're even willing to accept a negative expected return. You really have to think for this risk lover. The risk is a substitute for expected return. If he gets more risk, he's willing to give up expected return. And that can easily go negative. But don't get confused too much with that case. I mean, that's like a more theoretical case. Okay? So now, having learned that, we can actually create a portfolio, and this is actually where we started, that consists of one risky asset and one risk-free asset. So the risk-free asset is F, the risky asset is P, and now we want to learn or understand how much we should optimally invest in F and how much we should optimally invest in P. So everything we developed so far in the subchapter, especially the utility function, is a tool that will help us to answer this question. Okay? So in this example, let's say we have a risk-free asset that gives 7% or zero risk, obviously. But risky asset P, which can be anything, that can be a bond, a stock, a portfolio, think about it, it's what you want. That gives 15%, and has a risk of standard deviation of 22%. Okay? And we invest Y% in P, and 1 minus Y% here. So if we do that, we can quite easily, knowing what we know now from the portfolio statistics chapter, come up with the equations for expected return and risk of the portfolio. The expected return is again what? Well, it's just the weighted average. That's just the weighted average between the return of the risk-free asset and the return of portfolio P. So it's 1 minus Y times RF plus Y times RP. Always expectations. The way it is written here is exactly the same thing as a tiny restatement. It's written as RF plus Y ERP minus RF. It's exactly the same as I said before. So, but it's just a slight restatement. So here it's risk-free rate, and this is risk premium times the fraction we invest in Y. But at the end, it's just the weighted average. Okay, weighted average. We can set in the values, and we are done. What is the risk of this resulting portfolio? And we call this RC because C means complete portfolio. The complete portfolio is the portfolio that consists of the risk-free asset and the risky asset. So the portfolio that consists of the risky asset and the risk-free asset actually has a risk, the complete portfolio, of Y times sigma P, which is different from what we learned so far. There is no covariance term here, nothing. Why this holds, I will show you on the next slide. The core reason why it holds is that we assume that the correlation between the risky asset P and the risk-free asset F is zero. And this assumption is relatively reasonable because the risky asset always delivers the same return and the risky asset varies, right? So by definition, they cannot be correlated. And if we assume that here, we can relatively easily show that the resulting portfolio risk is simply Y times sigma P. So how can we do that? Well, let's start with the portfolio variance formula. This is the one that we know. That's what we developed earlier today. So then we set in the values for the complete portfolio and the risk-free asset and the risky asset. So 1 minus Y is A and Y is P. So this is sigma F and this is sigma P and so on. And we just set in the values here. Now we remember that the correlation between F and P is zero. So that actually means this 2AB term disappears because it has the correlation here. So that's zero, it disappears. So then we have the simpler term here. Then we remember, the correlation or the variance of the risk-free asset is by definition zero. That's how it's defined. The same in every state, in every line. So then this term here goes away, and we only end up with this term. So then sigma c squared is y squared times sigma p squared, so the standard deviation is simply the standard deviation of the risky portfolio times 1. Okay? Very simple. As long as we remember that the correlation between F and P is zero, and the risk of the risk-free asset is zero. So what we can then do is we can take the expected return formula here, RF plus Y, ERP minus RF, and instead of Y, we replace Y by sigma C divided by sigma P. So sigma divided by sigma P here, so Y equals sigma C divided by sigma P, and then you replace this here, and this gives us this equation. And then we set in the values. So it's 7 plus 8 divided by 22 times sigma c. So now we have an equation that tells us the expected return of the complete portfolio in relation to its risk. Expected return is 7 plus 8 divided by 22 times sigma c. Return relative to risk. The next step is to plot that. So how does this look like? 7 plus 8 divided by 22 sigma c. But that's a straight line with an intercept of 7 and a slope of 8 divided by 22. Right? So if we plot that, it's exactly this. It's a straight line that starts at 7%, this is the return, the risk-free asset. It has a slope of 8 divided by 22. Okay? So this blue line, this is what we call the so-called capital allocation line. And what this capital allocation line shows us is actually all risk return combinations that we can achieve in this world that only has F and P. Right? We only have F and P, but that doesn't mean we only have these two risk return combinations. Because we can combine F and P in portfolios. And we can invest everything in P, then this is return and this is risk. We can invest everything in F, then this is risk and this is return. Or we can split our money between F and P, then we are in between. Okay? Here everything is quite simple, it's a straight line, everything's linear, because remember, the risk of the portfolio here is just sigma times sigma P, Y times sigma P. In this special case, because the correlation between F and P is 0. So this capital allocation line now shows us in this world possible risk-return combinations. Okay? And some point on this line will be ideal, will be optimal for our investment. Which point we cannot yet say, but we are pretty close to that. So last question for today. At point P, we invest everything in P, in the risky portfolio or risky asset. How can we then realize points to the right of P? How can we realize these points? Yes, this is leverage. What do? We actually borrow money, right? We buy on margin. So points to the right of P means we are buying on margin, we are investing 150% of our wealth in P. And this is kind of coming back to what you asked earlier. If you are less and less risk averse and you're willing to take more and more risk, I mean, this is a straight line. The more risk you take, the more expected return you will get. I mean, of course, in reality, there are boundaries to that because you cannot buy on margin without limits and things like that. But conceptually, the more risk you take, the more expected return you will get. Not realized, but expected. Okay? So points on the blue line, possible risk-return combinations, we can realize all the points on this blue line. Which point our risk-averse investor will prefer, we will learn about that next week. Okay? Thank you very much.